In this lesson, we're going to enter the exciting, terrifying, and confusing world of recursion in computer science. Recursion is a powerful algorithmic tool that can be used to solve problems that can be impossible or at least very difficult to solve using traditional programming methods. We have a ways to go before we can get there, but a good example is the merge sort. Before we can tackle the merge sort, we need to get a basic understanding of the process of recursion. And we can look at that in the context of a problem where we can solve the problem using traditional techniques and then solve the same problem using recursion to see how they compare. Before we begin programming, let's look at a mathematical problem that could be solved using recursion. In math, the problem n factorial is expressed by taking the value n, which could be any positive integer, and then calculating its value by multiplying the value n. In this example, we'll say n equals 4, such that n equals 4 times 3 times 2 times 1, which has the total value of 24. So if n were equal to 5, we would add 5 times in there, and now this would have the value 120. For our examples, we'll stick with a slightly smaller factorial, 4, for our sample problem. So, let's begin writing the solution to this problem in Java. We'll begin by creating a new Java project, which we'll call RecursionIntroduction. Within that project, we'll create a public static void main class, and we'll also call it RecursionIntroduction. Click Finish to create the class, and as we've been doing, we'll delete the unnecessary comments, use the one remaining comment in the main method to fill in your name. Okay, so we're now ready to begin programming our method to calculate the value of any factorial number. So, first we use the keywords public and static, and then we declare the return type, which is going to be an integer, and then we must give our method a name, factorial, and finally include the parameters. In this case, the only parameter is the number that we're calculating the factorial of. We're going to want to have some variable that we can use to store our result, and in this case, we're going to give it an initial value of 1. And at the end of our method, we'll be returning that result. So we'll put that in now, even though we haven't actually calculated it yet. Now, interestingly enough, this would accurately solve the factorial if the number were 1, since 1 times 1 would be 1. However, it would be wrong for all other positive integers. So now what we need to do is make it so it will solve the remaining integers. And if we look at our mathematical problem here, what we do is we take the value and we multiply it times each lower value until the value gets down to 1. Notice that we're accumulating the total as we go. Another way to write this would be n equals 4 times 3 times 2 times 1 equals 24. Doing each of these problems one at a time, 4 times 3 would be 12, times 2 would be 24, times 1 would be 24, which would be our final answer. So we can accomplish that by writing a for loop where we have our integer I, or let's give it a better name. Let's call it multiplier. And we have to set its initial value. Now, if we imagine that our solution is going to be for factorial of 4, just to give ourselves some numbers to think about, what value would we want our multiplier to start off with? Well, if we're going to go from 4 down to 1, then we would want our multiplier to start off with 4, which would be the value held in number. So multiplier would start off with the value of number, and multiplier would continue, or our loop would continue to iterate as long as multiplier is greater than or equal to 1, because that's the final value in our factorial. And each time, what happens to our multiplier? Well, in each example here, our multiplier is going down by 1, which we can do by using the decrement command. Okay, so now all we have to do is modify result to take into account what we're doing. So we'll say result is equal to result times the multiplier. Now if we follow this code, if our number was 4, our multiplier would be 4, so our value here would be result of 1 times 4 would be equal to 4. That's what result would have. Then multiplier would become 3, so you'd have 4 times 3, which would be 12. Then multiplier would go down to 2, so you'd have 12 times 2, which would be 24. Finally, multiplier would go down to 1, which would give us 1 times 24, which is 24, and then we would return that result. Now we need to put the code into our main method to actually display this value. We're going to set this code up so that it'll be easier for us to debug and follow the code later on. So even though it's not necessary, we're going to break this down into several steps. First, we're going to create a variable for the number that we're going to do our calculations on. Number equals 4. And then we're going to set up another variable which will hold our answer. And then we're going to calculate our answer by saying it's equal to the factorial of our number variable. And then finally we're going to print that out in a nicely formatted output statement to the console. So we'll print number plus an exclamation mark equals plus our answer. Okay, so now we can run our program and see if our factorial method returns the correct number. 4 factorial equals 24, so our method has worked. Okay, hopefully this code is basic enough that you have followed along up to this point. Now things get a little bit more interesting because we're going to rewrite this method, or write a new version of the method, using the same concepts or different concepts to solve it using recursion. So we use the same keywords, public static, int, factorial will still be our name, but we're going to add a capital R to the end to indicate that this is the factorial version of our method. Otherwise, it has the same parameters. Okay, now, when we are solving a problem using recursion, remember that the basic structure is that we are trying to solve the problem by solving the same problem in a smaller form. And we keep solving the smaller form until we get down to what's called the base case. In this case, we can state the base case as being reached when number becomes equal to 1. Because in that case, we're multiplying by 1. So what do we want to do in that case? Well, all we want to do is return the value 1. Now we could have just as easily said return number, since we know number is equal to 1, but they say the same thing. And then we have to consider our non-base case. Well, that we'll cover in this simple algorithm using an else statement. And now we have to consider what we do when number is not 1. Well, by the definition of recursion, what we are trying to do is to solve the problem by solving a smaller version of the problem. So let's create a variable called current factorial, and we'll say that the current factorial is going to get a value equal to the factorial recursion of number minus 1. Now notice that we've defined our problem using the method that we're in the middle of writing. So current factorial will call factorial r, but with a value of number minus 1. So if it had 4 when the first method was called, it would come down here where it would have the value, it would get called with the value 3, then it would get called with the value 2, then it would get called with the value 1, at which point it would return 1. And that would be the base case having been reached. Okay, but we're not quite done. What do we do after we've calculated our current factorial? Well, next what we want to do is take number and set it equal to the value it currently has times the current factorial. And finally, we need to return a value. What do we return? Well, we return the current value of number. And we have now completely written a factorial calculation algorithm using recursion. Notice that there are no traditional loops in this solution. In our non-recursive algorithm, we used a for loop. In our recursive solution, there are no traditional loops. Okay, so let's now first check to see if our method works by changing our answer equals factorial number to use our factorial method. Run our code and see if we get the same answer. And look at that. 4 factorial is equal to 24. Now, you may be a little lost wondering exactly what's just happened. So, what we'll do now is we'll run through the code in debug mode and follow along and see what the computer's actually doing. So, I've put a breakpoint on line 6 of my code so that it will stop my program when it reaches that point. And then I'm clicking the debug button to run it in debug mode. Okay, now, we haven't discussed this yet, but over here in the debug section, it indicates that we're in thread main and that we're in the RecursionIntroduction.main method. That's important because what we're going to do next is we're going to step into the factorial method to see what it does. So I'm going to click the Step Into button. And when I do, I immediately come into my factorial R method, and I'm on line 17 of that code, where I'm looking at number. Since we were calculating the factorial 4, number has the value 4. Since number is not equal to 1, we will not be returning 1. Instead, we will be calculating current factorial by calling factorial R with number minus 1. So, what's going to happen here is that we're going to add another element to the stack here, another version of factorial R. We'll step into to see that happen. And as you can see, if you look at this code, I have factorial R still running, and on top of it, I have another factorial R. And in fact, we can click back between them to see the values. What's the value of number R in this top level of factorial R? Well, it currently has the value 3. But if I click back to this one, I'm not in the same method anymore. I'm in a older version where number has the value 4. Now I'm going to go back to the current version, which is where my code is stopped currently, and I'm going to step into again. Because my number is not equal to 1, I'm going to call factorial again, and so we'll see another factorial R get stacked on top of the existing one. This one has the number 2. And if I step into again, I will see that Now number is 1. How many versions of factorial R are actually running simultaneously? Well, if I look at the stack here, I can see that there's 4 of them stacked on top of each other. Now, since number is equal to 1, what value will be returned by this method? Well, obviously, it's going to return 1. And at this point, I've just lost one of my factorials off the top of the stack. So number currently has the value 2 here, and we're now ready to calculate current factorial. So I'm going to step, and I can see that current factorial has the value 1 because that was the value returned, and I'm now going to multiply that by 2. So number now has the value 2, and I will return that. And I've lost another one of my recursive methods. In this version, number has the value 3. What will be the value returned by current factorial? Well, it'll have the value 2 returned, as you can see. And we'll multiply 2 times 3 and assign that to number, so number will become 6. And that value will get returned to the next element of the stack, which is going to be another version of factorial. In this version, number has the value 4, and the factorial that's returned is 6. So now we're going to take number, multiply it times 6, which will give us the total of 24, which we will return, and we're back in our main method, and we can now assign the total of all of the recursive calls to factorial R to the variable answer. And so answer gets the value 24. And then we output that value, and our program has run its course. I'll switch back to the main Java view and run it just one more time at full speed. As you can see, 4 factorial equals 24. And if I change number to a different value, like 5, I will get 5 factorial equals 120. So now you've seen a factorial solution to, or rather a recursive solution to calculating a factorial. Does it make sense to write this code using recursion? Well, the truth is that this code could be written in either way and would essentially be almost equally efficient. You might look at our factorial solution and say, but there's all these extra lines of code. However, many of these are unnecessary. I split these up into separate lines. If I wanted to, I could shorten this by simply saying return factorial number minus 1 times number. This one line of code would eliminate these 3 lines of code. And now if I look at the 2 methods, I can see that they're about equal in complexity and length. So this is an example where recursion doesn't necessarily make our solution easier, but it certainly doesn't make it any longer either. Okay, so let's look at another potential problem that we could solve using recursion and see if you can get a little bit of experience with it. So, what if I wanted to calculate the power of any given number? I want to know what 4 to the power of 4 is. Let's write that code using our traditional programming methods. So, our keywords stay the same. We'll call our method power. And in this case, we have 2 arguments, the base and another integer which represents the exponent. So, how do we solve this problem? Well, once again, we're going to want to create an integer to store our result, and we'll give it an initial value equal to base. Then we write a loop where we iterate over all the values of exponent, and each time we multiply the base times itself. So when we're done, we have to return our result. And now we have written a method that should calculate any exponent base pair. So let's try it. Let's do we'll say answer equals power of number comma number. So that would calculate 4 to the 4th power, and then we'll output the result. So in this case, we'll output number, and traditionally when you're expressing an exponent in computer languages, they use the upward pointing caret symbol to indicate power of. Okay, so now we can run our program, and we see that 5 factorial of 120 is 5 factorial equals 120. 5 to the 5th power is 3125. Let's set our value back to 4, run it again, and we can see 4 to the 4th is 256. Let's put a real simple one to check to see if our program's working. 2 squared is in fact 4, and of course 3 to the 3rd power is 3 times 3 times 3 should be 27. So we can see that our traditional programming solution using loops has solved our power problem. Now begins your challenge. You need to write a recursive solution to the calculating a power problem. Good luck.